Welcome back. And the topic this week is us continuing the discussion of this specific algorithm, which is called the variational quantum eigensolver, which is the standard way by which we today solve eigenvalue problems on a quantum computer. And this is essentially the project one, which deals with the quantum computing aspect. Then for project two, we can see where your interests go, whether you would like to do quantum machine learning, or you would like to look at specific algorithms within quantum computing. Quantum Fourier transforms is one topic many people are interested in. But what we are going to do today now is simply to look at how we implement this for the 1 and 2 qubit Hamiltonians. And then we are going to look at the Hamiltonian, which has been extremely popular in physics, and it's called the Lipkin model. This is contains some physics jargon in the beginning, but at the end, the kind of Hamiltonian you are going to look at, or the matrix you're going to diagonalize, is going to look like the matrices which we have seen for the 1 qubit case and the 2 qubit case. Now, one of the things which we discussed last time was, why do we measure on 1 qubit only? And why do we insist on rewriting these combinations of Pauli matrices in terms of Pauli X, Pauli Z, and Pauli Y matrices? And then we perform the measurement using this Pauli Z matrix, which then has eigenvalues given by the eigenvalues of the computational basis. And our computational basis is qubit 0 and qubit 1. So the reason why we do this is deeply connected with the experimental setup, the way you perform a measurement and the way you act on a physical system. And you can actually, with many of the standard probes, like a magnetic field, that is something which can be simulated mathematically with this Pauli X, Pauli Y, and Pauli Z gates. So the actual process of measurement is reflected in the mathematical equations which we are setting up. So I just wanted quickly to remind you a little bit about the VQE algorithm. So VQE is a variational quantum eigensolver. And here are some basic readings. And this review article of Tilly contains, if you look into section 7, that contains a good discussion of the classical optimization part. And some of you are probably very familiar with the optimization part, starting with Newton's method. And then you have everything from the standard gradient descent, where you update the second derivative, or the learning rate, as we call it in machine learning, with root mean square propagation, Adams, etc. Or you can use some of the quasi-Newton methods, like Broyden's method. There is a Broyden-Farberg, Goldberg-Shano method, which is a very popular one for finding the minimum of a function, or roots of a function. So that classical part is something which you would implement on a classical computer. So this algorithm is a hybrid, because the algorithm which was proposed in the beginning, which is called the quantum phase estimation algorithm, leads to very long chains of Pauli X and Pauli Y and Pauli Z matrices, which again means that many of the physical systems which you have available do not have these long simulation times. So that means that the algorithm becomes impractical on the actual quantum computers which we are building nowadays. And that's why this VQE has popped up as an intermediate step, where you do some parts on the quantum computer, and then you have a classical part which is run on a classical computer. Actually, this is a very interesting research project nowadays, is how to link a classical computer with existing quantum computers. There is actually a company in Finland, which is called Algorithmic, which was established by an Italian physicist, Sabrina Maniscalco. And this company delivers software solutions where you match a classical high-performance computing facility with a quantum computer. So you need actually software which makes the two talk together, so that you can run some parts of the calculations on a quantum computer and some parts on a classical computer. And that's going to be a kind of hybrid mode, which will be very, very important in the next 10 to 20 years before you have a full-scale quantum computer which replaces the standard high-performance computing facilities. So this is just to show you some of the perspectives and why this is a very interesting algorithm by itself. So the kind of idea, now we do a reminder from last week. So an algorithm which we will discuss a little bit later, because we need to introduce quantum Fourier transforms in order to understand that algorithm, was the phase estimation algorithm. This algorithm is actually not very practical for the kind of applications on standard quantum computers. So the VQE, while this algorithm is provably efficient, the variational quantum eigensolver represents a kind of hybrid in what we normally call the noisy era of quantum computing, because many of these quantum computers are actually plagued by noise. That means noise means actually interactions with the environment. Just to give you an example of a typical thing which can go wrong when you run on a quantum computer. So if you're dealing with a supercomputing qubit technology, then the machine is typically cooled down to almost 0 Kelvin, close to minus 273 Celsius. However, when many people are operating on the machine, then you can get thermal excitations. The thermal excitations can actually ruin your computational basis, and your expectation values are just garbage. So you would see that if you make a measurement on these Bell states, where you should get 50-50 as an output for a measurement, if many people are running on it, they actually have to rescale the machine, which in principle means to cool it down again, so that the computational basis is restored. That's a typical example of what can go wrong with quantum computers nowadays. And so that's why this VQE has become so popular, and people are running many of these standard quantum physics applications in quantum chemistry, in atomic physics, in molecular physics, etc., on quantum computers using the VQE. So the basic principle is the variational principle. So this is nothing but your eigenvalue problem rewritten. So you have to find the eigenvalues of this matrix. And there's something which is called the Rayleigh-Ritz variational principle, which simply states that for given Hamiltonian, the expectation value of a trial state or just ansatz puts a lower bound on the lowest lying state. So if you go into textbooks on, let's say, linear algebra and eigenvalue solvers, you will see this Rayleigh-Ritz quotient, as it's called, this expression on the left-hand side. So the typical ansatz is to parameterize your state in terms of some angles. You perform rotations, and then M is now the number of optimization parameters. And this is where you have the optimization problem. So which means then, just to quickly repeat, we now look at the Hamiltonian and a given state where you now have these thetas as our optimization parameters, is that you can show that if you expand this one in an eigenbasis, then if you leave out the denominator in the Rayleigh-Ritz ratio, you can actually show that the minimum value here, obviously if you have the exact eigenvalues, then there will only be one specific state which pops up. And you are going to minimize the problem with respect to the angles theta in terms of optimizing this problem here. And that's essentially the basic philosophy of the VQE algorithm, which means that you would start by preparing a given state on a quantum computer. And this can be done by these rotation operations, which are unitary operations. Then you would measure this circuit in various bases and send these measurements to a classical computer. The classical computer post-processes the measurement data to compute the expectation value, and it also finds the optimal values here. And you would continue that loop till the gradients go to 0. So this is a kind of overview which we looked at last time. So the points in yellow here are typically done on a quantum computer. So you would perform the rotations, prepare the state, and then you perform a rotation measurement of the different Pauli strings. Now, this is then fed into the optimization part where you're actually calculating the different gradients, and you have an analytical formula when you're performing operations with the rotation matrices, which is then given by the expectation value of the Hamiltonian of an angle plus pi half, and similarly for an angle pi minus 1/2. So that gives you the gradient, and then you use your favorite algorithm to update the gradients. Okay, so I wanted to repeat some of these topics. Why do we measure on 1 qubit only? Because if you have a matrix and you diagonalize, you get the eigenvalues and the eigenvectors, and then you have the information about the system. Now, when we do this with a quantum computer, you're actually measuring on one specific qubit at a time. And there are several reasons for that. So many of the algorithms are actually algorithms which act on only one qubit at a time. And some of the algorithms need only some partial information, like in Shor's algorithm. If you look at the collapse and entanglement, when you measure qubit, then it collapses its state. So potentially affecting entangled qubits. And sequential measurements then allow extraction of information while managing entanglement. Measurement basis, this is something which is very important for us. Most algorithms use a computational basis. And in our case, we have a computational basis, which is given by some specific states of the system. So when you think of the states 0 and 1 for 1 qubit, they define our computational basis. And this computational basis is often defined in accordance with the type of physical system which you have available. So you can find specific states which you can identify and manipulate by lasers or magnetic fields, etc. And essentially, when you do the measurements, you're acting on the system with some device. That can be a magnetic field, it can be a laser, etc. And then when you act on one of the states, then the state can go back to its ground state or fundamental state by the emission of, let's say, a photon. So these are called single photon emission processes. And many systems in semiconductor physics, they actually have these properties. And they can then be candidates for making such computational basis states. So this means that if you're doing a joint measurement in an entangled basis on more than just one qubit, that can actually require complex setups and are not always needed. So when you run the experiment, you could think of having two isolated systems, and you know experimentally that now I can act on one of the systems and perform my measurements on that. So many of the algorithms are rewritten so that you act on one qubit at a time. And there is, in the case which we are looking at in eigenvalue computations on a quantum computer, there is actually an algorithm which is based on you being able to measure on a single qubit. And the consequences for us is that we want to rewrite many of the measurements in terms of that basis. So we have crosstalks and noise. So there's a simultaneous measurement risk, which can disturb neighboring qubits due to hardware imperfections, and especially in the type of devices which we have now. So I mentioned this case with the superconducting qubit quantum computers, where if many people are operating on the system, then the system gets heated up because it's cooled down to very low temperatures. And that means any disturbance can actually heat up the system and ruin the computational basis for it. So there are many of these considerations, they have to do with the way we implement it physically in a physical setup. There are also some readout constraints. So the physical implementations may have a limited readout bandwidth, which actually enforces sequential measurements. Readout is one of these technically very delicate topics. We are not covering this. So but I want to give you this as a background for why we have these specific approaches. Then there are some other resource management. Sometimes you want to reuse qubits, and there's something which is called ancilla qubits, which we haven't discussed, which are used in error corrections. They are measured, reset, and reused. So while joint measurements are theoretically possible, the dominant practice of measuring one qubit at a time stems from algorithmic adaptability. Many of the algorithms act on one qubit at a time. The hardware limitations and the need to minimize quantum state disturbance. So if the systems are well isolated, you could think of acting with a laser on one of the subsystems without affecting the other one. So what I want to do now, just switch quickly over to the Jupyter notebook. No, sorry, to the whiteboard, and just remind you quickly of what we did with the one qubit case, so that we have that more clear and ready for us when we jump into the two qubit case. So let me just go back to the Jupyter notebook. No, sorry, not the Jupyter notebook, the whiteboard. Here we are. So if we look back at what we did last week, so there's an element of repetition still. So one of the things which we looked at last week was actually to have a system, a one qubit system, where we then have a Hamiltonian, which could just be given by a Pauli Z gate. So there's a C1, which is a constant. And then the VQE ansatz means that we have a trial wave function. And then we have the expectation value of the energy, which is simply given by this quantity. And if you only have the Z gate, then you are calculating the expectation value of that operator. So this shorthand which you have here is essentially this physics-like way of writing an expectation value, which in standard statistics courses you would see written in this specific way. So this is the mean value, and this is the quantity we want to calculate. Now, what we ended up with then, when we looked at this type of operations, was that if we now look at this specific state, this psi of theta, where theta is now the parameter we want to optimize, this is something which we could write out in terms of a complex constant alpha multiplied with a computational basis qubit 0 and a complex parameter beta. So this is just a superposition. So when I then calculate the expectation value of the energy, which for this very, very simple case is the same as this expectation value here, that is nothing but this quantity C1, which is just a constant in front of the Hamiltonian. And then I have the complex conjugate plus the complex conjugate of beta, or 1. And now I have to multiply this with the operator C. So that's a Pauli Z matrix, which, just to remind you quickly, is given by 1, minus 1, 0. And this is multiplied with 0 and alpha plus beta 1 here. And this gives us, when we look at it, it gives us then alpha squared minus beta squared. And this is multiplied with this constant C1. Now, the way we measure is that we perform a given set of measurements, and this could be M measurements. Of the system, and that means that we would measure qubit 0, and that is simply the number of times we measure 0, M0 divided by M, and then we have beta 0, beta squared, which is the number of times we measure qubit 1 divided by M. And that means that the final expectation value, which we have for the energy, is something which we will approximate now with a C1 multiplied with m0 divided by m minus m1 divided by m. So when we have this variable number of shots, that simply stands for the number of times we do the measurement. So when you do this physically in the lab with an experimental setup, you repeat this m times. So it sounds strange, but you're actually doing m experiments. And then you hope that when m becomes large, that you can invoke the law of large numbers and that you then are approaching the correct value. This is essentially what we do. So that means that when we set up this type of values, we also have to calculate the variance of the expectation value. So we cannot provide only the mean value, but we also need to provide the expectation of the variance. Now, we're going to be a little bit sloppy in project one, but if you do this as a true experiment and you run a theory calculations on top of that, then you always have to provide the variance on the data. Because else you will just get your results back and people will simply tell you, give me the standard deviation. You will be surprised to see how many scientific articles actually, which are submitted, tend to forget about that. Now, so let me just go quickly back to the basic way by which we set it up in the code. And you can use these codes as an example when you write your own projects. So let's just go back to the Jupyter notebook. And there is a code example which I used last week. And in that code examples, we are essentially implementing the VQE. And let me just bring that up here. So this is the first part is this 1 qubit case, which is a 2x2 matrix. And here in the first step, I'm simply defining my Hamiltonian as a function of this parameter lambda. And then I diagonalize. So this is just me calling a standard eigenvalue solver, which you see here immediately. You see now that as soon as I've set up the Hamiltonian, I can then find the eigenvalues here by lin alg eig. So this is pretty straightforward. And you would need to do that for essentially all the algorithms which we have. And in this particular case, what happens is that we start here with this parameter lambda equal to 0. So this state is our lowest lying state, is the qubit 0. And this state is qubit 1. And the gap here of 4 is simply because we decided E1 to be 0 and E2 to be 4. So there is no interaction. And then we switch on the interaction, which now gives us these matrix elements here. And when I diagonalize, as I turn on the interaction here, then this state changes character, and here it's actually turned into qubit 1. So this is normally called an avoided level crossing. This is not so interesting for us. What is interesting for us then is actually the way we now set up our quantum eigensolver with a VQE. So there is a library which you can find here, which sets up a 1 qubit state, a 2 qubit state, and prepares your states. But you can see now that I define the Pauli matrices, the identity matrix. These are 2x2 matrices, as you can see. This is my original state. And then I perform a rotation, Rx and Ry, as we discussed last time. And so my new state is actually equal to this rotated state here. And then I can get the energy, and now I'm setting up my energy parameters, these constants, different constants which I have. I set up the measurement because now it contains a Pauli X gate as well. And here I have to transform it with a Hadamard gate to make the measurement in the Pauli C gate. So one is a direct measurement in the Pauli C gate, and the other one is a transformed one where I take the state and I act with a Hadamard gate, which is included in this function QC here, which you have access to when you go to the Jupyter Notebook folder. You will then see there's a QC pi here, which sets up some of the basic functionalities of setting up a 1 qubit state, a 2 qubit state, etc. So feel free to use these codes when you're developing your own code. And now I'm setting up the expectation value for the energy. So I need that one. But then, since I'm doing a optimization, I need now to implement my gradient descent. Everything is run on a classical computer here. But ideally, you would run this part here, the measurement of a Z and X on a quantum computer. And you would perform this prepare state on a quantum computer. But then, when you then have the energy, you see now that I'm calculating the parts of the gradient, so the gradient here. And in my case, it's a 1-qubit case, so I have an angle theta and an angle phi as the parameters I want to optimize. And what I've implemented here is a simple gradient descent. It's a stochastic gradient descent, so I do it by number of iterations, and then the energy difference is larger than 10 to the minus 4. So this is a convergence criterion which I plugged in. And then I get my new energy, which is now given, so I'm just accumulating the different values. I set the number of shots to be 10,000, so I'm doing this 10,000 times. I have my learning rate, which is the parameter I multiply the gradient with. So this becomes a parameter we normally fine-tune, unless you want to use a more advanced method. So you can see now the minimization here is a method now which is defined by us. So this is just setting up the gradient. So this is the classical part here. So we will be calling the quantum part, where we initialize everything and we perform the optimization. Alternatively, and this is something I would recommend for project 1, instead of using your own gradient descent, you're fully allowed to do that, obviously. It's more fun. But you can also use the minimization functionality which comes with scientific Python. And in that specific case, what you would need to set up is the method. And in this particular method, we use the Powell method. You can use Broyden's method. You can use Broyden, Fletcher, Goldberg, Shannon, which is a very popular way, which is a so-called quasi-Newton method, where you don't need to evaluate the second derivative of the gradient, of the energy. So when you use Newton's method now, you're not finding the roots of the energy, but you're calculating the roots of the gradient, because that's the quantity you want to find the roots of. So that means in Newton's method, instead of the first derivative, you would have the second derivative to invert. And since you have many parameters, this becomes a matrix. This matrix is called the Hessian matrix. And that is a quantity when you have many parameters, which you typically don't want to evaluate, because if you have 10 parameters, the Hessian matrix would be a 10 by 10 matrix, which you have to invert. So in every iteration, you have to invert a matrix. So this method like Powell or Broyden's method, etc., these are methods which approximate the Hessian matrix. And we're not going to cover them, but I would normally recommend using this scientific Python methods from SciPy, and one of these is actually the minimize function in SciPy. When you do that, what you end up with, as you can see here, actually this solver SciPy is a little bit more stable than the brute force which I had, where I put in by hand my learning rate, which replaces the second derivative by a parameter. And you can see that my SciPy is actually doing pretty well. So is also my code. But in general, this is the results you would get for the lowest lying state. And remember now that this is a variational approach, and that gives you the lowest energy of the system. Any questions so far? Okay, so what we're going to do now is to switch to the 2-qubit Hamiltonian. And then we need some extra laboring here. So in this case, and this is in the project, we have a Hamiltonian which looks like this. And we have a diagonal term, which we can think of as something which does not involve the interaction. So I'm just rewriting the diagonal ones in terms of these guys here in much the same way as I did for the 2 by 2 matrix. And then you can then show that this H0 can then be written out in terms of these different matrices. So I have a identity times identity. I have a C tensor product with an identity. And then I have C tensor product C and X tensor product X. Now, what we want to do now is to make a measurement on the first qubit. And this part here acts, the Z matrix acts on the first qubit. So what we are going to do now is to look at some of these matrices and why we, from a computational point of view, as we did when we go back to the one qubit case, we made a measurement in these spaces, the Z matrix, which is represented by the computational basis, but then we transformed the poly X to a poly Z by performing a unitary transformation with the Hadamard matrices. So what we are going to do now is actually to look at how we can transform all these other matrices, except the Z tensor product I, into something which looks like that. So this is a kind of a thing which you end up doing when you're implementing the variational quantum eigensolver. And you will see when we come to this Lipkin model, we are going to have strings of 4 poly matrices. And we have to rewrite them in terms of something which looks like a Z and tensor product with a series of identity matrices. So I'm going to try to step you through these details and how that actually, happens, that we end up there. But let me just quickly switch now to the not that one. Here we are. So I'm switching a little bit between the Jupyter notebook and the whiteboard and the slides. So in the measurements, what we are doing then is that we want now to transform the original string, which is P. So that's some combination of poly matrices. We want to find a unitary transformation, which then transforms this into this basis M, where M represents the gate matrix which performs the measurement. And this is often given by a poly C matrix. So we often say that we are doing a poly C measurement. So you already seen, so we will typically have a string of poly matrices. And every Hamiltonian of a system is something which we at the end rewrite in terms of these matrices. And that is because we are going to make the measurements. The external probe which apply to the system can look like a poly matrix. And that means that we try to transform the Hamiltonian in a string of poly matrices. And when we have that, we would like to find a way to perform a measurement. And we're going to make a measurement on 1 qubit at a time. So the poly matrices, one of the ways you can do that is to use these commutation relations between the matrices. And you can also use the fact when the matrix squared is equal to the identity and with that relation. And what you would typically do is to group terms that are easier to measure together. And one of the things we have already met is actually this term here, where you have a poly X matrix. And since we have this basis here, we can just perform a Hadamard transformation. And then we can transform a poly X to, in this case, X is equal to Hadamard times Z times a Hadamard. And this is what we did. So the matrix which we're going to start with is actually this one. So this is the first part of the Hamiltonian which we rewrote. So that has a poly Z times the identity matrix. So the identity matrix is just ones. So in the first block, we just get ones, and then we have minus ones here. Yeah. Exactly. Yeah. So if you now look at your basis, the important thing now, and we are coming back to this on the whiteboard, if you look at this specific matrix here, if I act on 0, 0, so let's do that. And you will then see that when this acts on the computational basis, because now I have 2 qubits, it's not a 1 qubit case. So my computational basis, which is also, if I go back a little bit, this computational basis is also an eigenbasis of this H0, the diagonal part. And that means that one part of the Hamiltonian can actually be solved exactly. So if I act on with this one on my computational basis, what we are saying now is that we typically perform a measurement in the Pauli Z basis. So this is equivalent to performing a computational basis measurement. So you can see that immediately. If I multiply this 0, 0 state with the matrix, I get the 0, 0 state. If I act on this state, which is the 1, 0 state, so let's just do that on the whiteboard here, because that's a little bit easier to see. What we will see then is the following. So let's just do that. So if I now take my Pauli Z times the identity matrix, so both of these are 2 by 2 matrices, and this is given by 1, 1, 0, 0. I'm just putting a 0 here, and -1, -1, and 0, 0. If I act with this one on my, so let's do that. -1, 0, 0, -1. If I act on this one with the 0, 0 state, where that state is nothing but this vector, 1, 0, 0, 0. This gives me +1, 0, 0. So this acts on the first qubit, okay? If I then perform the action of this one, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, -1, 0, 0, 0, 0, -1. And if I act on the state, which I called 0, 1, so what that means is that I've changed the second qubit to 1. If I look at that one, that gives me also +1 of 0, 1, 0, 0. So in a certain sense, this is also an eigenstate with eigenvalue of 1. Now, if I take the next one, so now I'm just going to write Z times the identity matrix, and I act with this one on 1, 0. And remember that that one is 0, 0, 1, 0. What happens then is the following. I'm now performing a measurement. If I perform a measurement on the first qubit, which is because I have this Z matrix here, you see now that what I get is -1 times 1, 0. So this is a correct eigenvalue when acting with Z. If I take only Z, and this acts on qubit 1, and on qubit 1, this is the same as -1. So qubit 1 is now in state 1, and when I act with this matrix, I get the right eigenvalue. So for my computational basis, when I make the measurement in the computational basis, I get the correct eigenvalue. Now, if I then look at the next one, see why, and this acts on 1, 1, you will see that this is given by -1 of 1, 1, which is also correct. So if I'm making the measurement in this specific, with this specific matrix in a specific basis of qubit 1, I'm getting the correct eigenvalues of the states, the computational basis states which I've taken. However, if I look at the next term, and after that one, we're going to take a small break. So if I look at my 1Z matrix, so let's just set that one up here. Let me just find my notes here. So if I take the next part of the Hamiltonian, which is 1Z, this is going to be given by 1 of -1, 0, 0, 0, 0, and then I have 1 and -1. So I actually have, this is something I can write in a more compact way as a poly Z, 2 times 2, a 0, 2 times 2, 0, 2 times 2, and a poly Z, 2 times 2. Now, if I now make the measurement, so pay attention to what happens now. So if I make a measurement on the first qubit, 0, 0, this gives me plus 0, 0. So that is okay. Okay. But if I make a measurement on qubit 1 changed to state 1, so this one, what I get then is plus 1, 0. And that is wrong, because when I'm acting with a poly Z matrix on qubit 1, I should get -1. So this is not correct. So what I want to do then, so the plan is to actually rewrite this one through a unitary transformation and then perform the measurement in a C times 1 or identity matrix. So what I can do then, if I look at this C times I, which is the matrix I want to perform my calculations in, this is something I can rewrite in terms of a unitary transformation times this matrix times U here. Now, this unitary transformation is in our case given by what's called a swap gate. And I'm going to stop pretty soon now. And that looks like 1, 0, 0, 0. And now let me just get it right here. And then I have 0, 0, 1, 0, 0, 1, 0, 0. This matrix is very interesting because this is used to entangle states. And you can see that now because it swaps states. So if I act with the swap matrix on the state 0, 0, I just get back 0, 0, so nothing happens. If I act on this one, on the state 0, 1, I swap bits. So that's why it's called a swap matrix. So when they are the same, 0, 0, they just stay 0, 0. And if I act on this one, 1, 0, that swaps 1 and 0 again, and I get that one. And that is equal to 1, 1. So if you do the algebra, if you have a, let's say, a tool like Octave or Python on your laptops, you can simply just punch in this matrix, punch in the Kronecker product here, that is just in Python, this is just the Kronecker product, and then perform the operation. And then if you subtract this side from that side, you should get exactly 0. So it's useful to do that test yourself. So one thing is just to see the matrices, but another one is actually, so when I started to look at these topics, I actually did all these matrix and matrix vector multiplications just to gain some confidence. So these operations which you then can set up. So that means that that specific string in the Hamiltonian which we have and now we just take a small break. So that specific string, which we have in the Hamiltonian, if we now go back, it means that in our Hamiltonian here, I can now rewrite. I keep this one as it is. I'm going to keep this one as it is. This doesn't change anything. This does a measurement in the C basis. And this one is something I will now change with a unitary transformation. So after the break, we're going to look at how to change this one and how to change that one. And then we have everything ready for running a computation for these different parts of the Hamiltonian. So what we do when we measure, we actually measure each of these individually. And then we just add them, and then we have the final expectation value. And that's the way, if you run an experiment, this is the way it's done, experimentally. Except that we don't need to bother about that. Yeah.
So we have Z connected, so fully Z connected to identity.
Yeah.
And then we apply this to different states. Then you said that this is the right value. So that
yeah. So let me just repeat that one. So the question is, if we now go back to the whiteboard, if we now look at if we go back a little bit and we look at the states which we have here, when I act on the different states here, I know that when I act on qubit 1 with C, so C acts on qubit 1, which is this term here. So let me show you that here. So here we should put a subscript 1 and here a subscript 2 to indicate that this acts on qubit 1. And you see that when that acts on qubit 1, we should get -1. So that's correct. If I take an act on this one, so when qubit 1 is being acted upon by this one, I should get plus here, which is correct. And the other one's also correct. But if I then look at this one and I act on this one, so now it's only the identity which acts on qubit 0, then I get plus. But now it's the identity, so if I make a measurement on this qubit, in my computational basis, this is wrong because it should be minus. Because if I look at my computational basis states, the action of, if I'm making a measurement with a C matrix, you see now that I don't have a C matrix here. So I should have gotten, ideally, I should have gotten a minus here, but I'm not getting that. And that's why I want to transform it. I want to transform this one into that form. And then I make the measurement. So if I take the original expression, which I have, this one, and I can actually show this, that this is given by this swap matrix, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0. And then I multiply with the matrix which I had here, C, and then multiply again with the swap matrix. So I'm simply performing a unitary transformation on my Hamiltonian. That leaves the eigenvalues unchanged, the unitary transformations. And this brings us back to the form which I want to have, so that I have a poly Z, which now acts on my computational basis. So my computational basis is Z. So when I measure on qubit, on the first qubit, the computational basis is given by these two states. So if I act with C on 0, so this is how I make my measurement, because I can now have a magnetic field which is actually given by a Pauli C matrix. So I'm actually performing a measurement on the first qubit. So you could think of you having a system where you have particles here, and this can be thought of as indistinguishable systems. And now I want to make a measurement only on this one. So that's why I want to change all these operators in the correct order. And you see also that if I act on qubit 1, and this is my computational basis, I should get eigenvalues which are either +1 or -1 when I act with Z. So this is my external probe. So what I'm doing now, I have a Hamiltonian which is written in a way which is unwanted because I have this term here. But now I'm performing a measurement on qubit 1. And when I perform a measurement on qubit 1, I want that eigenvalue here to be minus. But I don't get it when it's in this specific form. So then I transform it back to the way the measurement is being done in the computational basis. Did that help? A little bit? Yeah. Yeah. So let's take a small break. So what we're going to do now is to look at some of these operations which we need to do. And we're also going to introduce these as specific gates acting on the system. Because till now we have just been looking at the 1 qubit operations. And we have introduced these 2 qubit gates a little bit earlier, but I'm just going to remind you of the way they look like, and also the way you can draw the diagrams for these type of gates, because there are different conventions. And when you run software like PennyLane or Qiskit or similar ones, they will typically just draw the gates for you, which you're setting up before you make a measurement or when you want to make a measurement. So let's switch over to the whiteboard rather quickly. So one of the gates which we also need to look at, now we looked at this one tensor product, identity matrix tensor product with Z. But in the Hamiltonian which we had, we also had an X tensor product with X, and we had a Z with a tensor product of Z. So these are also gates which we want to transform into this gate which looks like Z times a string of identity matrices. Now you could actually make a calculation in that specific basis, Z times Z, and you would get the correct values for 1 qubit. But I'm going to tell you a little bit why later, why you normally rewrite this one as well. So the expressions are given in terms of specific gates. So we met before the break, we met this swap gate. So let's just put some question marks here. So how do they look like? So ideally, there should be a transformation here for XX, where we now transform it into this basis. And then there is another unitary transformation, CZ, where we take the same and UCC. So the question is, what do they look like? Now, I'm just going to set up the expressions for you, and then we are going to implement them in the code thereafter. And I will try to, next week, I'm going to tell you a little bit more about the algorithm itself of finding this unitary transformation. So now we're just going to think of this as something magic, which is given to us. But then we need to rethink a little bit and see how we can generate this for a more general case, because now we are specializing this to a 2 qubit case. So the Hamiltonian contains these type of matrices. It's a 4x4 matrix. So before the break, we looked at the swap gate. this is also something which can be represented graphically. So this was given by 1, 0, 0, 0, 0, 0, 1. No, sorry, not like that. 1, 0, 1, 0, 0. And that has the important task of transforming or flipping bits. Now, this is often written graphically in a specific form. So let's just write that one down. Let me just see where I put up my notes here. Here we are. So the swap gate, if you now have a qubit 1 in a specific state, so we begin with that one, and then we have qubit 2 in a specific state, then one way of drawing it is like this. So you swap the bits. So this becomes psi 2, and this is psi 1. So we swap the bits. When you have 0, 0, when it acts on 0, 0, it leaves them unchanged. If it acts on 1, 1, you're still getting 1, 1. But if you act on 0, 1, you get 1, 0, and vice versa. Now, this is also written graphically in a compact way like this. So this is a kind of way you will see this being pictured in textbooks like that. So these are two equivalent ways of drawing that specific gate. Now, if we look at the C tensor product C gate, or C part of the Hamiltonian, that has a specific transformation, which we are now setting up here. So let's just bring that one back. So when I look at the Z times Z, this has a specific mathematical form, which looks like this 4x4 matrix, minus 1, 0, 0, 0. And it's part of the Hamiltonian which we have. And you see now that when I act with that one with those specific states which we had, you will get the correct eigenvalues actually. But it's common to transform this one in terms of the following. So this matrix UCC, which we discussed, is going to be given by a specific matrix, which is called CX10. So let me say a little bit about this CX matrices. This is a 2-qubit operation. It looks like as follows. So let me just write it down here. I just have to find my notes here. And this is given by the following: 1, 0, 0, 0, and 0, 0, 0, 1, 0, and then 0, 1, 0, 0. So this is part of a set of gates, part of gates called control gates. And there are many of these gates. So let me show you some of them. So if I do that transformation, if I take the emission conjugate and multiply with the C tensor product C and multiply again with the matrix here, then I'm going to get this C matrix tensor product with the identity matrix. So that is one type of transformation I can do now. But let's now make a small digression and look at these control gates. So these are 2-qubit gates where we can perform operations on matrices. So there is one which is called the C0 gate. This is a standard one. And the C0 gate is something which you will also see written as a control X gate. And it's common sometimes to add a subscript, 0, 1. So let me show you what this looks like. So mathematically, it looks like 1, 1, 0, 0. And then I have a Pauli X matrix. So you would often write it in a more compact way like this. So you have the identity matrix, 2 by 2, 2 by 2, a 0, 2 by 2, a 0, 2 by 2 here. And then you have a Pauli X, which is a 2 by 2 matrix. So what is this gate doing for us? So if I act with a Pauli, with this control gate, what we would get then is the following. So if I act with C0 on 0, 0, this is the same as taking this matrix and acting on the vector 1, 0, 0, 0. You will see that that just gives back 0, 0. Nothing happens. If I act with the 0, 1 here, that gives me simply 0, 1. However, if I act on 1, 0, I get 1, 1. So that means that if the first qubit is in state 1, then I'm actually changing the second qubit. So we have a C0 here. If I act on 1, 1, that becomes equal to 1, 0. So you see qubit 1 is left unchanged, but qubit 2 is then changed, depending on the value of qubit 1. So if qubit 1 has a value 0, nothing happens. If it has a value 1, then it changes the value. So graphically, you would see this written in the following way. So this C0, or just the CX, which is another way of just labeling it. And you see now that you can set up different types of gates. You can set up a CY, a CZ gate. So we're going to look at them. So graphically, you would often see this written like this. So this is the first qubit. And then we have a Pauli X operation like this. So we would call this the control qubit. And this would be called the target qubit. So I can then change. So if control qubit is equal to 0, nothing happens. With qubit 1. 2, which is the target. So this is a way of performing a NOT operation on a 2-qubit state. So if the control is equal to 1, then qubit 2, the target, changes. Okay. So this is one type of operation. We have other types of matrices which you can encounter and which are part of this type of unified transformations which we're interested in. So we have a control C gate, which is often written just as a C. And that has a drawing which looks like this. So we leave the control qubit open. And then we have a C gate here. And the standard way of writing is, you could also see this one written like this. This is another way of seeing that same gate. And I just leave that to you to actually play around a little bit with what it gives as an outcome. So you can take the C on 0, 0 and just see what that gives. You can take CZ acting on 0, 1, etc. And I leave that as a small exercise. There's also another gate which is interesting to look at, and that is the Hadamard gate. So we can have a control. You can set up different types of control gates. And in that case, what you would have would just be something like this. So you have the control qubit here, and then you have a Hadamard gate here, and like that. So that's another type of gates which you can set up. And in that case, the way you would write it up then is through a matrix, which you would call CH. And that is going to be given by the identity matrix, 2 times 2, 0, 2 times 2. And then you have the Hadamard matrix, 2 by 2 here. And you can then set up different operations. So if you look at the Hadamard gate, you can now look at the operations it does on different 2-qubit systems. So if I do a C Hadamard on 0, 0, since I have the identity matrix on top there, this just gives 0, 0. If I take the Hadamard gate on 0, 1, that is also acting on the first qubit in state 0. This also gives back 0, 1. But then, if my first qubit is in state 1, this is now going to give me an entangled state. So this is one way I can make entanglements. So that is going to give me the state 1, 0 plus 1, 1. So this type of operation, the Hadamard gate, is also something which we can implement as a physical process. And similarly, if I take C of 1, 1, you will see that that also gives us an entangled state here. I'm going to get 1, 0 minus 1, 1. So these are two entangled states which I now can create by performing this type of operation here. So where the first qubit is not acted upon, but then depending on the value of the first qubit, I can then create an entangled state. So as a typical example, you could now look at a specific process where you have 2 qubits. And essentially, this is what we are going to do now. So if you look at a 2-qubit system, as an example, you could think of now performing 3 types of operations. So let's look at this 2-qubit system. So the state which we start with, so we would have an initial state here. And we could say now that we have a psi. This is qubit 1. We haven't specified it. This qubit 1 could be in a linear combination of 0 and 1. And then we have a state phi. So this is our 2-qubit state. And then we perform some operations here. So the first type of operation which we could do is to perform a Hadamard. And then we could do the same on the second qubit. So these would be separate operations on each qubit. So this gives us now a psi 1. And then I have a psi 2 here. We can call this for stage 1. And in this specific case, what we have is a type of operation where we now are transforming our state by a specific process, which I'm going to call for G1, which is simply going to be given by 2 Hadamards. So I write it like Hadamard times Hadamard. Then what we could do next is to perform a control NOT operation. So we could now have this, and then we have a control NOT. So that's a CX operation. So this is stage 2 here. And in that case, we have a G2, which is actually given by this CX, the control not gate. And now I have my psi1, which is unchanged. Nothing happens with that. But my state here, actually, sorry, this should be, I wrote this wrongly here. Sorry for that. So this should be phi1, not psi1, sorry. And here I get phi2. And then I could think of performing yet another operation where I could have a new stage 3, where I do a new Hadamard and a new Hadamard here. And then I end up with a final state so that at the end, what I have, so this G3, so the stage 3 here, could again be a G3, which is a Hadamard times a Hadamard. So my final state, which then is a psi3 with a phi3. So in this specific case, this is equal to psi2. So they are the same. This is again given by psi3, hence a product with a phi3. We could write this out as G3 multiplied with G2 and multiplied with G1 and multiplied with the initial states, which are psi and phi. So what we would have then is a series of operations where we now have created entangled states. The Hadamard gates gives us a superposition. And depending on the type of measurement we want to do then, we have different types of final gates which we are looking at. So the type of operations which we need to do depend obviously on the type of Hamiltonian which we have and how we want to perform the measurements. So here I've just set up the circuit by looking at the final state. There is no measurement here. So afterwards, we could now think of this as a 2-qubit state, which we have prepared for final measurement. So if you then look at this gate which we have, when we are now performing the calculations, so let's look at the explicit evaluation, explicit measurements. For the 2-qubit states. So what I'm going to set up now is my expectation values. So we need to calculate. So we have a qubit 1 in the final stage. And let's just call this psi1. And then we have a qubit 2, which is now phi2. So this is the final qubit 1. And this is the final. And they will depend on different parameters, qubit 2. And they depend on four parameters, on 4 angles. So I would typically prepare the states by making rotations on the states, 2 angles for the first qubit and 2 angles for the second qubit. Then I need now to calculate this quantity here. So in this quantity here, I'm actually in the computational basis, which I'm interested in. So I don't need to do anything. Okay. My next, however, when I take the term, which is I, tensor product with Z, I need to perform a transformation here. So what I need then is to calculate psi1 and then phi2. But now I have this transformation where I have U, and this is multiplied with Z times the identity matrix, multiplied with U, and then psi1 and phi2, and where this one is a swap gate. Then the next ingredients which I need to look at are actually X tensor product X. In that specific case, I can rewrite X in terms of a Hadamard. So this will involve the Hadamard gate, which means that what I end up with is the following expectation value. So let's just set that one up here. I should have it. Let me see where I have it. Okay, let me just find my notes here. There we are. So this one requires now that we make a measurement in the final states, but where my U matrix now has to be transformed. So what I need to do is to take this control NOT, control X gate. Oops, not that one. Look. Just rewrite it. So I have a CX10, the one we put up earlier. And this is multiplied with a Hadamard because we need the Hadamard gate when we transform the X gate into the computational basis. And then we have a C times I and multiplied with a CX10 and then the Hadamard. And this is then multiplied with psi1 and phi2. So that's a little bit more involved. And so that means that we need to make a further transformation of the state psi1, phi2. So typically, if you look at this state now, which we have the final one, before we perform the measurement, so I would start with some state, let's say initial psi0, and then I have an initial phi2, phi0, and then I would perform a Rx, I would perform an Ry on that state. I would do the same here, an Rx and an Ry. But then to perform this final operation, I would need a new transformation, which I'm just going to label as a U here. And this gives me psi1 and phi2 here. And this U, which you see here, is simply this ugly object here. And now you see quickly why, when you run this type of computations on a real quantum computer, you're actually setting up gates which perform these operations, which means that somewhere in here, there is some external field like a laser or magnetic field or whatever you're using. What is your experimental limitation? And then you are simulating this type of operations on your physical system. For us, it just suffices to set up these specific matrices and then just perform the calculation. So from a theoretical point of view, life is much, much easier, as it always has been. And we can quickly jump from one problem to the other one, whereas an experimentalist is just confined to the equipment which you have. There's a privilege being a theorist. Okay, so you see, this is the way we would then prepare the state. And after that, then we would perform the measurement. And the measurement would then be performed with this object which you have here. And finally, let's set up the final one, which we need. So this is the C times C here. And in that specific case, what I need is my psi1, phi2, the two final states. And now I need to perform a new type of operation, which is now given by this CX10 matrix, which we put up. So I have a CX10, and this is then multiplied with Z cross the tensor product with the identity matrix and CX1 and acting on psi1 and phi2. So that's the final piece which we need to deal with. If we then go back to the code, which you have access to in the Jupyter Notebook, then you will see how we actually implement these different types of operations, measurements, when we do the final evaluation of the expectation value. So let's just switch back to the Jupyter Notebook. So all these operations which you see here, the strings of the different Pauli matrices, everything you've seen on the whiteboard is actually given in the Jupyter Notebook. So you can try, and I normally recommend people actually to try it out and set up these matrices and see that these transformations actually give you what you expect. And basically all these terms are discussed here in the Jupyter Notebook. And you can perform the transformations, and you can easily see that this ZZ matrix gives you, when you perform these multiplications, it gives you actually this matrix which you want to have. So any unitary transformation of such matrices also describes two half spaces, which are labeled with eigenvalues. If you look at this one, that follows from the identity that C is equal to a Hadamard times X times a Hadamard. And similar to the one qubit case, all two qubit Pauli measurements can be written in terms of unitary transformations. And this is essentially what we've been doing now. So there are more examples. Explicit, these are the explicit expressions which we need to deal with in that part of project one. And this contains a more complete list of all the possibilities which you can have. Because there is nothing which hinders you of having an imaginary part in your Hamiltonian, because your Hamiltonian is in principle given by a measured matrix when we have a discrete basis. And that means that you can easily have a Y tensor product Y matrix and so on. So I'm just leaving this for the sake of completeness. But for the project which we have, now this is the thing we have to plug in. And you can see now these are the energies. And what you see here, the first one is just us calling the standard eigenvalue solver, setting up the Hamiltonian or the Hamiltonian matrix, as we call it, because we have only four states, the four computational basis states, 0, 0, 0, 1, 1, 0, and 1, 1. And then we do a simple diagonalization. So this is not very fancy at all. And we then get, as you can see here, when you move down, I'm now setting up the diagonal parts of the matrix, which are then given in terms of this Zi. So you see a Kronecker delta of Z and I. I'm setting up the measurements in this IZ basis. I have the measurement in the CI. I have a measurement in the CZ. And finally, so you see now I'm doing a Hadamard and then the C0 10 gate. So I have predefined these ones in this file, which is called QC, which you have access to. So I'm setting up all these operations here. And now I have transformed my basis states. And then I measure XX, measure CZ, CI, IZ, and I also have the identity which I need to add. And then the energy minimization runs as before. So this is my own handwritten one. I do just a number of shots, 1,000 experiments. I have 5,000 iterations. I have a learning rate, and then I'm simply setting up the lambda values, which are these interaction parameters. And then I calculate the energies as before. Alternatively, and which I normally recommend, is to use a scientific Python with a standard minimization algorithm. And this is the optimization part. And here I put 10,000 shots. And you can see that the eigenvalues, these are the analytical ones. And if I go down a little bit, you will see now a pretty good correspondence for the lowest lying state. And this is my scientific Python result. And that's essentially the, the benchmarking of my system with the variational quantum eigensolver. But you see that it depends on the number of times of measurements you make, the optimization algorithm, all these results, or all these ingredients will actually influence your final result. But since most of you are pretty familiar with the optimization problem, you know that is actually parts of the bottleneck. Any questions so far? So this gives you essentially the recipe for the 1-qubit and the 2-qubit Hamiltonian. And then we are going to transfer this one to a model which is called the Lipkin model. Now, this is something which I need to say a little bit more about. And I see we only have 4 minutes left here before the end. So what I will do is to dedicate next Wednesday fully to a discussion of that model. Now, this model, in the slides you see here, there are more details than what you need. The important thing is that we can rewrite this Hamiltonian in terms of Pauli X, Pauli Y, and Pauli Z matrices. So what we are going to have, and I'm going to give you the basic message, and then we discuss a little bit more the physics, because the physics here deals with the particles which are called fermions, which are particles with spin half, like an electron or proton or neutron can have. And these are intrinsic degrees of freedom. And the first part here is more meant as a reminder to people who are aficionados of many-body physics, because it starts from a totally different point of view. And in many-body physics, it's pretty common to rewrite things in terms of something which is called creation and annihilation operators. So this is jargon. You don't need to think of that. What's important for us, and I'm going to put that on the whiteboard here, is the following. So in a nutshell, the Hamiltonian which we are going to diagonalize for this specific Lipkin model and next week I'm going to, so I put in a lot of background, which is totally unnecessary if you're not interested. So the Lipkin model itself has a Hamiltonian, and we are going to define something which is called spin 1. And I will say a little bit more about that next week, because I need to give you some background so that you have a basic understanding. But many of the technicalities you see in the slides are technicalities which I brought in in order to show how you can derive the form which you will see here. So this Hamiltonian is going to be given as follows. So we are going to look at both j equal 2 and 1. This is given by a constant, epsilon divided by 2. There is a sum over I, which is the number of qubits which we have, or the number of particles. So we can just put, so n stands for the number of qubits, which is going to also be loosely translated into the number of particles. And this is given by a stream of Pauli C matrices. There is a new term where we have a sum I less than j, so this is a double sum. And we have a Pauli X times a Pauli xj matrix minus yi and yj. And then there is a new term, so there should be a minus sign here, sorry. And next week, I'm going to give you some of the physics background for this. But if you're not interested in that, we can just think of this as a string of Pauli operators. And these strings of Pauli operators are then going to represent the type of Hamiltonian which we want to simulate. Actually, there are many Hamiltonians which can be directly translated in terms of poly X and poly Y matrices and poly Z matrices. Because that's the language we speak when we want to implement things on a quantum computer. If you're diagonalizing a normal standard diagonalization algorithm, we don't need to care about this. So this is a Hamiltonian which has been very popular in physics simulations. It carries a lot of the kind of physics degrees of freedom you expect in a many-body system. It has nice analytical solutions, and it's also a system which can be diagonalized easily. So, but for us, this is the model which we will start with. But next week, I will try to give you a kind of a more coherent derivation of that. You don't need to look at all the details because the slides contain much more details than are needed, and they are more targeting people who have some knowledge in many-body physics. But for us, this is where we will start and look at things from a computational point of view next week. And this is the final part of project 1. But if you have the 1-qubit case and the 2-qubit case, what we are going to need then is just to set up operations on strings of qubits. Now, one thing you will see is that if you have 2 qubits, then you would just have an xi and an xj. But if you have 4 qubits, this acts on only 2 qubits at a time. So that means that this operator, which you see here, will have to include combinations of identity matrices because 2 of the qubits are not acted upon by the Hamiltonian. But we're going to look at that in more detail next week. So for this first case with j equal to 1, that's something we will translate into actually a 1-qubit system. In principle, for j equal 2, this is something which we will have to translate into a 4-qubit system. But we will look at these details next week. I hope you see the wood for the trees and that the 1-qubit case and the 2-qubit case, that you see how you have to implement it, because that's an essential part of the first project. And the final one is just us applying this to something more not exactly realistic, but something which simulates a more realistic physics system. Then after project 1, the idea is that people can choose more paths they want to follow. So some people have been looking at Fourier transforms and quantum Fourier transforms. Other people have been interested in quantum machine learning. And then there are other options as well. Any questions so far? Take a small break, is that okay? Okay, let me just stop the recording then.